The James Webb Space Telescope has once again forced humanity to confront a universe far stranger than imagined. In what seemed like a routine observation, Webb turned its massive gold-plated mirrors toward a patch of sky that appeared unremarkable. What it revealed, however, has left astronomers and physicists shaken. Instead of faint smudges of light or primitive star clusters, Webb captured images of galaxies, vast, massive, and fully formed, existing only a few 100 million years after the Big Bang. These structures are not supposed to exist so early in the timeline of the cosmos. Their presence challenges everything we thought we knew about how the universe evolved. According to the standard cosmological model, the early universe was a turbulent and chaotic place. Matter was still spreading out, cooling, and only beginning to condense into the first stars and proto-galaxies. Theories long suggested that true galactic structures, the kind with spiral arms, enriched chemistry, and black holes at their cores, required billions of years of gradual growth and mergers. Yet Webb's images defy that. They reveal galaxies as massive as the Milky Way appearing just 300 to 400 million years after the universe began, complete with complex structures and evidence of multiple stellar generations. The very existence of such galaxies introduces problems that ripple across every corner of astrophysics. Star formation, for instance, has natural bottlenecks. Radiation pressure from the first stars, along with violent supernova explosions, should have slowed down the accumulation of new stars. Instead, these galaxies show signs of stars being born, living, and dying at speeds that appear impossible. The detection of heavy elements like carbon, oxygen, and iron within them suggests that stellar cycles had already played out multiple times in what should have been the blink of an eye cosmologically. The universe, it seems, wasted no time in building complexity. Perhaps even more unsettling is the evidence that supermassive black holes already occupied the centers of some of these galaxies. According to conventional wisdom, black holes grow slowly, starting from the remnants of massive stars and building mass over billions of years through accretion and mergers. Yet here, in the infancy of the universe, we find them already millions or billions of times the mass of the Sun. To explain this, theorists are considering exotic alternatives, such as direct collapse black holes formed instantly from enormous clouds of primordial gas, or primordial black holes seeded directly by fluctuations in the infant universe. Even so, the scale and timing strain the limits of imagination. The implications reach beyond black holes and star formation. They call into question the very timeline of cosmic evolution. If galaxies of such maturity were already present so early, either the processes that shaped them occurred with a speed and efficiency never accounted for, or the physics governing the early universe operated under principles we do not yet understand. Some researchers suggest that dark matter or dark energy may have played roles far different from their expected ones, accelerating structure formation in ways beyond current models. Others dare to ask whether general relativity itself, the foundation of modern cosmology, might require modification to account for these findings. Another startling possibility is that time itself flowed differently in the early universe. If relativistic or quantum gravitational effects altered the passage of time during those dense, high-energy conditions, then our conventional assignment of 300 million years after the Big Bang may not reflect the same duration as we understand today. This radical idea, once dismissed as speculative, is gaining traction as evidence continues to pile up that defies the established framework. The discovery also disrupts the long-accepted theory of hierarchical galaxy formation, which holds that small clumps of matter merged gradually to build larger galaxies. Webb has instead shown us giant, fully formed systems appearing with no obvious precursors. This hints that under certain conditions, large structures may emerge independently and in parallel, bypassing the slow, incremental growth previously assumed. The sheer number of these galaxies compounds the mystery. Webb did not uncover just a rare anomaly. It found many, in just a tiny sliver of sky. If they are this common, then our models are not merely off by a margin, they may be fundamentally flawed. For decades, the cosmological constant has been treated as the steady driver of universal expansion, tied to the mysterious phenomenon we call dark energy. Yet if the early universe produced galaxies so rapidly, perhaps dark energy did not behave as consistently as once thought. Its strength or influence may have shifted, altering how quickly matter gathered together. That possibility undermines one of the cornerstones of modern cosmology, forcing theorists to rethink what controls the balance between expansion and structure formation. Equally puzzling is the orderliness of these early galaxies. Instead of chaotic blobs expected in such a turbulent era, many already show disks, bulges, and even spiral-like features. Dust lanes weave through some, suggesting multiple stellar generations had already lived and died. This level of organization implies stabilizing mechanisms that should not have been available so soon. To see such quiet maturity in a universe still thought to be violent and unstable is one of the most confounding aspects of Webb's discovery. The consequences are not limited to theoretical debates. If galaxies formed earlier and matured faster than once thought, then the potential for planets, and perhaps even life, may also have arisen far sooner in cosmic history. Entire civilizations could have had time to rise and fall long before Earth was even formed. The philosophical weight of that possibility is immense, reshaping not only scientific understanding but humanity's perspective on its place in the cosmos. What Webb has revealed is not a minor adjustment to existing theories. It is a rupture, a challenge to the scaffolding of cosmos. If primordial black holes turn out to be real and widespread, the entire cosmic timeline might be far more compressed and dynamic than we've long assumed. The James Webb discoveries are also forcing scientists to rethink the role of dark matter, that mysterious and invisible substance making up about 85% of the universe's matter. Dark matter is essential in simulations because it explains how galaxies hold together and how they form at all. Yet if galaxies are appearing earlier and faster than simulations predict, then perhaps dark matter has properties we have not yet included in our models. It could interact more than expected, or clump more aggressively in the early universe. That possibility points toward new paradigms such as warm or self-interacting dark matter, which would radically reshape the cosmological picture. There is also the tantalizing chance that what we are witnessing is the fingerprint of unknown physics at work in the early cosmos. Exotic particles, hidden dimensions, or modifications to the nature of gravity itself might be necessary to explain the data. Ideas that once lingered on the theoretical fringes, such as variable speed of light theories, scalar field cosmologies, or even cyclic universes, are suddenly being re-evaluated with fresh urgency. What seemed speculative yesterday may now be essential today. This discovery also creates tension with what we know from the cosmic microwave background, the faint afterglow of the Big Bang recorded in exquisite detail by missions like COBE, WMAP, and Planck. That ancient light provides a picture of the universe just 380,000 years old, setting strict limits on its density, temperature, and smoothness. But Webb's discovery of massive, structured galaxies just a few 100 million years later seems incompatible with those constraints. Reconciling two precise yet apparently conflicting datasets may become one of the most formidable challenges modern astrophysics has ever faced. The James Webb Space Telescope itself is emerging as more than just an astronomical tool. It is a true paradigm-shifting device for humanity. After years of delays and difficulties, its ability to peer deeper into time and space than any previous instrument has inaugurated a new era of cosmology. And astonishingly, these discoveries may represent only the beginning. The deeper Webb looks, the more anomalies it uncovers, threatening to unravel the narrative of cosmic history we thought we understood. Beyond theory, there is something profoundly human in all this. For centuries, every leap in our understanding of the universe has come from moments of disruption. The move from an Earth-centered cosmos to heliocentrism, from Newton to Einstein, from a static universe to the Big Bang. Each breakthrough was born in uncertainty, when new observations broke the spine of old models. We may be standing at another such turning point today, when the universe itself forces us to rethink reality. These galaxies are not just ancient light, but messages from deep time, carrying secrets across billions of years only to shatter our assumptions. They reignite the spirit of science itself, the restless drive to push beyond the boundaries of what is known. But the questions they raise cannot be solved by any one field. Physicists, cosmologists, computer scientists, and astronomers will all need to collaborate, running new simulations, building new instruments, and testing ideas once dismissed as fringe. There is also something poetic in what the early universe is telling us. The assumption has long been that simplicity must precede structure, that order comes slowly after chaos. Yet Webb shows us that complexity may have been present from the very beginning, that the cosmos could have erupted like a symphony already in motion rather than a slow unfolding crescendo. As the telescope continues its mission, more light from these ancient epics will pour in. Each observation has the potential to overturn what we thought was certain. The galaxies that shocked physics may only be the first chapter, with stranger and more baffling phenomena waiting just beyond the reach of current instruments. Perhaps hyper-dense clusters, voids of unimaginable scale, or structures that bend time and space in ways that seem impossible. In this lies the audacity of the universe. Just when we believe we are close to understanding its origins, it hands us a mystery so profound it makes our best theories feel like sketches on the margins of truth. And in doing so, it reminds us that science is not about reaching the end of knowledge, but about embracing the vastness of what remains unknown. The Webb telescope has not only revealed galaxies, but it has reawakened the sense that physics itself may be incomplete. Our equations rest on assumptions about symmetry, entropy, and time, but what if those rules are not universal? What if they are statistical averages rather than hard laws? Perhaps in the young, energetic universe, star formation, time itself, and even causality operated differently. Some scientists now suggest inflation, the period of exponential expansion after the Big Bang, may have left behind regions of unusually high density, where matter collapsed rapidly into galaxies. Others wonder whether quantum fluctuations localized certain areas of space with different initial conditions, meaning the universe we observe is just one of many possible versions. This even strengthens arguments for a multiverse, where the laws of physics vary across different regions of reality. There is also the possibility that particles or forces existed in the early universe and later vanished. These hypothetical influences, sometimes called early dark energy, could have accelerated structure formation before fading away, leaving behind only their effects on the galaxies Webb now reveals. If so, then we are glimpsing a chapter of cosmic history that cannot be